Hello friends, today's question. A uniform solid cylinder of density 0.8 gram per centimeter cube floats in equilibrium in a combination of two non-mixing liquids A and B with its axis vertical. The densities of liquid A and B are 0.7 gram per centimeter cube and 1.2 gram per centimeter cube respectively. The height of the liquid A is HA 1.2 centimeter and length of the part of the cylinder immersed in liquid B is HP, that is 0.8 centimeter. So we have to find out three things based on this question. First is find the total force exerted by liquid A on the cylinder. Find H, the length of the part of the cylinder in air. And C is the cylinder is depressed in such a way that its top surface is just below the upper surface of liquid A and is then released. Find the acceleration of the cylinder immediately after it's released. So this is the basic diagram which is given. So we have a cylinder and it is basically divided into three parts. One is in air of height h, another is in the liquid A of height HA, and the third part is liquid B, in liquid B rather, and the height of the cylinder in liquid B is HB. So in part A, we are supposed to find out the total force exerted by the liquid A on the cylinder. Okay. So let us solve part A. So for this particular part A, we can draw a rough approximate diagram. So this is a cylinder and this is our part A. And in this part A, you can see that the pressure due to the force, due to the liquid rather, is exerted on the surface of the cylinder, or we can say it is radial and symmetrical. So as the pressure is radial and symmetrical, therefore the net force that will be exerted by this radial and symmetrical pressure will be equal to 0. So we can say that pressure exerted by the liquid A on the cylinder is radial and symmetrical. So therefore the net force, which is nothing but the total force, is 0. So the part A was quite simple. And now let us solve for our part B. Part B, we are supposed to find out the height. Find H, the length of the part of the cylinder in the air. Okay, so we have to find out value of this H. And it is given in the question that the cylinder is equilibrium. Okay. So we can say that cylinder is in is in equilibrium under the action of three forces. Under the action of three forces, and the three forces will be, first will be the weight of the cylinder, second will be the buoyant force because of liquid A, and the third will be buoyant force because of the liquid B. Okay. So we can say weight of the cylinder cylinder, let us call that WC, and we can find out that our WC will be equal to rho C multiplied by G and multiplied by VC. Okay, where rho C is the density of the cylinder, and VC is the volume of the cylinder. VC is volume of cylinder, and that volume of the cylinder will be equal to AC, that is area of cross section of the cylinder, multiplied by L, and L is the length of the cylinder. We can say AC, area of cross section of cylinder, and L is the length of the cylinder. Length of cylinder, and that will be equal to H plus HA plus HB. So we have assumed that L is the length of the cylinder, so this is our L. So obviously L will be equal to H plus HA plus HB. So we can write that our volume will be equal to AC multiplied by H plus HA plus HB, and we can substitute volume of the cylinder in this equation, and we can write that our WC will be equal to, rho C multiplied by G, and we can write this as H plus HA plus HP multiplied by AC. Next force is our buoyant force because of liquid A. Buoyant force due to liquid A, let us call that FA, and FA will be equal to density of liquid A multiplied by G, and the volume that is being associated with liquid A, that is our VA. So we can say rho A is the density of liquid A, density of liquid A, and VA is the volume of the cylinder that is associated with liquid A, that is associated with liquid A, and that will be equal to our AC, area of cross section, and the height that is associated with liquid A. So we can write our buoyant force Fa will be equal to rho A multiplied by G multiplied by AC and multiplied by HA. So we found out the weight and the buoyant force with respect to liquid A. Similarly, we are going to find out buoyant force because of liquid B. Buoyant force due to liquid B, let us call that FB. So FB we can write directly based on FA also. So FB will be equal to rho B multiplied by G AC, and we have this HB. And equilibrium, weight will be acting in the downward direction and both buoyant forces will be acting in upward direction. So this is upward direction, this is also upward direction, and weight will be in downward direction. So we can write at equilibrium WC will be equal to FA plus FB. We substitute the value omega C WC rather was our CH plus HA plus HB multiplied by AC, and we have here rho A G AC HA plus rho B G AC and HB. G and AC cancels out. So we get from here that our H so we can write this as H plus HA plus HB is equal to rho A multiplied by HA plus rho B multiplied by HB divided by rho C. And we are supposed to find out value of H, so we can just write it now. H will be equal to rho A HA plus rho B HB divided by rho C minus HA plus HB. Now we know all these values. We substitute the values. Rho A is given as 0.7 and this is about 0.2 plus 1.2, and we have 0.8 divided by 0.8 minus 1.2 plus 0.8, and if we simplify it, we can get this as this will be 1.4 and this will be our 16 and 96. So we get this as let me check, I think it's 1.2, sorry, 1.2, 1 second. Density liquid is rho A 0.8, and we have liquid A and B. Rho A is 0.7, it's correct. HA height is 1.2 and rho B is 1.2 and HB is 0.8. Yeah, it's correct. So therefore, if you solve it, this will be coming as 0.25 centimeters. So this will be the height of the cylinder in the air. This is the height of the cylinder in the air. Next, we are supposed to find out if part C, we solved part A and part B. Part C says that if the cylinder is depressed in such a way that its top surface is just below the upper surface of liquid A and is then released, find the acceleration of the cylinder immediately after release. So we can just try to redraw the figure again for this particular part. So we are in part C, and it states that if this is our surface of liquid A, then the cylinder is depressed such that the top part is just touching the surface A. So initially, this was a position of the top part and it was having height h, which was in contact with the air, and this was our liquid A and this is our liquid B. And initially only this part was for HB. Now as it is depressed below, an extra H part will be added into the liquid B. So we can just redraw this figure. We can say that if this is our liquid B, extra portion, now the cylinder will be something like this, and extra height of H will be with respect to liquid B. So we can say that when the cylinder is depressed, is depressed so that the top of it is just below the surface A, below the surface A, the additional upthrust is only due to the additional upthrust is only due to the additional volume, and that volume will be H multiplied by AC submerged in liquid B. Is the additional upthrust is only due to additional volume H multiplied by AC submerged in the liquid B. Okay. So in the liquid B, there will be extra volume, and that volume will be equal to height H, which is the extra height, and AC, that is the area of cross section. So therefore we can say the net upward force, you can say net upward force will be equal to extra upward thrust on the cylinder. Extra upward thrust on the cylinder, because previously the cylinder was in equilibrium. Now as the equilibrium disturbed by applying extra force on the cylinder, So therefore there will be net upward force acting on the cylinder, and that net upward force will be only because of the extra upward thrust on the cylinder, and this extra upward thrust will be because of this additional volume H multiplied by AC. Okay, so we can say extra upward thrust will be equal to area of cross section is AC, H density of the liquid B, and multiplied by G. So this will be equal to the net upward force. Okay. And if A is the acceleration, we can say if acceleration is given as A, then this A will be equal to net upward force divided by the mass of the cylinder. Net upward force divided by mass of the cylinder. And net upward force we just calculated. So we can say this will be equal to net upward force is our area of cross section AC, H rho B multiplied by G, and mass of the cylinder will be equal to area of cross section AC. Total length of the cylinder is H plus HP plus HA multiplied by rho C. That is the density of the cylinder. And AC cancel with AC, and we substitute the values. H we just calculated is our 0.25. Density of the liquid in the liquid B is 1.2, and this is given as G, and H plus HB total is 2.25 and multiply by 0.8. So if we solve it, this will be giving us as 0.3 multiplied by G and divided by, it will be coming as 1.8. So from here we can say G divided by 6. So therefore the acceleration A will be equal to G divided by 6. This is the acceleration of the cylinder when immediately after it's released. This is the and it will be unit will be centimeter per second square. Acceleration of the cylinder immediately after its release, and its direction will be upward. So this completes the C part also of the given question. Okay, so this completes the question. Thank you.